Hello everybody, my name is Felix Eyben. I'm a scientific employee at the Institute of Steel Construction by Professor Feldmann from RWTH Aachen, and I will present some interesting things on experimental and numerical investigations on the rotation capacity of high-strength steel beams, which we did in a research project called STROBE with my colleagues Schaffrath and Helen Bartsch. So the motivation is to use plastic design for steel structures, for example like this frame. With that you can utilize your cross sections, for example by reducing the cross section dimensions, or to get higher load bearing capacities. By that your structure gets more economic and environmentally friendly. So first of all, what is the plastic global analysis? It is stated in Eurocode 3 part 1.1. And it allows to consider effects of material nonlinearity when calculating action effects. As example, the plastic hinge approach. I will show you the formation of a plastic collapse mechanism. For this simple example, two-span beam with a concentrated force in the middle of the left field. This is the resulting moment distribution for the case that P is in the elastic range, so we get an elastic moment over here. In this diagram we will measure P and the rotation phi, which is the end beam rotation. And if we increase P, we will stick to the point that we reach the plastic moment here in the field, so the resistance moment from the cross section. And in the diagram we assume, okay, at this point we will have the first hinge in the field. So at this point we assume that we can't get higher moments than M plastic, and we can rotate. So we assume that there will be this plastic hinge, and we have this new structural system. And for this new structural system we can increase P, and we get the plastic resistance moment over the column or the support. That is where the second plastic hinge forms, so here over the support. And this structural system is now kinematic, so we found our ultimate load bearing capacity from the system. This approach is a realistic determination of the load bearing capacity and leads to a more economic design, and we can utilize our cross sections better. It is stated in Eurocode 3.1.1 and Eurocode 3.1.12 that the plastic global analysis can be applied for conventional strength steels, but not for high strength steels, which are from the Eurocode 3 part 1.12, which is between 460 and 700 megapascal. The prerequisites for a plastic global analysis: you have to have a class 1 cross section for conventional strength steels. Class 1 cross sections are able to withstand the plastic resistance moment and to reach even higher moments and to reach this sufficient rotation. And for the web and the flange there are slenderness limits given in the Eurocode, which is mostly the C over T ratio, and the yield strength is taken into account about the epsilon. Additional, the stability of members has to be guaranteed, so no lateral torsional buckling, and there are also additional regulations referring to the application of stiffeners. The last point, which is indirectly checked over the cross-section class, is sufficient rotation capacity of the members has to be ensured, and I will define the rotation capacity in a minute. So what's rotation capacity? It is assumed that class 1 members for conventional strength steels show a sufficient rotation capacity. We can determine that by experiment. We have a 3-point bending test. We record the end beam rotation and the force P. In the hinge model, analogously to the plastic hinge approach, we assume in the middle we have the plastic reached, and then we have here a hinge. So in the diagram we have the straight lines over here for the hinge model, and we see that the experiment reaches higher values, and the rotation capacity is defined between this first and the second point, and we divide the rotational angle here over the free plastic, and then we have this unitless definition of the rotation capacity. and it is good for comparison reasons, and in the background document it is stated that 3, the value of 3 is the requirement for class 1 cross sections. And it is also shown that different systems require actually different rotation capacities if you use the plastic hinge approach. For example, this system over here requires only a rotation capacity of 1.3. As I said, the plastic global analysis is not allowed for the high strength steels because they are assumed to have poor rotation capacities. And these points prompted us to investigate the existing rotation capacity and load bearing capacity of HSS beams. On the one side experimental, and to recalculate it numerical to extend the database. So this leads me to the experimental investigations. The goal was determining the rotation capacity of HSS beams and investigate the rotation behavior. We did 20 experiments with welded eye sections, which we can see over here. We conducted 3-point bending tests, and in series 1 we investigated 10 tests of homogeneous beams. 2 was made of conventional strength steel just for comparison reasons, and 8 was made of S690. In series 2 we had 10 tests of hybrid beams where the web is made of S355 and the flange is made of S690. 2 lengths was investigated and the beams were laterally supported. Here's our test program. In addition to the material, we can see that we varied the flange and web slenderness to get the influence of the cross-section dimensions, and the length varied the moment gradient. All cross-sections were in cross-section class 1, and we measured the imperfections before the experiments. So our test setup, we did 3-point bending tests. The lateral supporting was depending on the length, and the loading was applied by displacement control. So in reality, for the S355 beams we didn't have lateral supports, while for the short beams we had 4 lateral supports, and for the long beams we had 8 lateral supports. The load application was via the pin directly over the stiffener in the middle, and over the supports were also stiffeners. And the lateral support looked like this with this roller construction, so the beam was allowed to do vertical deflection but no lateral deflection. We measured different things, so we had inclinometers here at the end to measure the end beam rotation. We measured the applied force and the vertical deflection, and also used strain gauges to verify our numerical model later. We, from this data, created force displacement curve, which we transformed into moment rotation curves. And we see here the moment over the rotation. And I will show you one example curve for a specimen from specimen 103, which was made of an S690, a short one, and the plastic resistance moment of this cross section was about 440 kN. And we see that first we have this elastic range, we reach the plastic resistance moment, the beam didn't really show great deflections, and then we get into the plastic part until we reach the maximum. And here we see that small buckles form, and we had some visible deflections. After the maximum, the deflections were even higher and the buckles start to form until the beam cracks in the tension flange. And this was a typical diagram for experiment. And we then did the normalization to M plastic and Phi plastic to determine the rotation capacity, as we see over here. And we can then determine the rotation capacity. It was 4.3 for the specimen, which is bigger than 3, the requirement by the Eurocode. The determined rotation capacities were nearly all above 3, only 2 beams didn't reach the value of 3. The conventional strength steels, the S355, reached much higher rotation capacities, and all beams reached the plastic resistance moment. We also see that the hybrid beams here reach higher rotation capacities than the homogeneous high strength steels. If we look which two beams are the one which doesn't reach the three, that are the ones with the most slenderest webs. So in general, our conclusion is that HSS beams are able to reach a sufficient rotation capacity for plastic design. After that, we modeled the tests numerically with the FEM software Abacus, and the cross-section geometries were exactly like in the tests with the welding and also the stiffeners. We used a calibrated material, which was a true stress strain curve, which we calibrated at the experiments and tension tests. We added the loading and supports exactly like in the test. And for our mesh, we used a bias function, and we also included imperfections to get the realistic results. We also implemented a damage criterion based on Johnson and Cook, which looked like this as plastic strain over stress triaxiality, and this was determined at the experiments. We first created individual damage curves for each cracked beam, and we see that the results fit very well. So the individual damage curves are validated. We needed to use an average damage curve because we can only use one damage curve for the material, and we have some deviations over here, but mostly on the conservative side. So in general, our average damage curve is also validated. The validation of the numerical model, so the moment rotation behavior fits very well. Also the deformation and buckling looks very good. And also the crack initiation point and the growth could be represented very well by our numerical models. This leads me to our conclusion. So we did investigations on the rotation capacity of HSS beams. Most beams are able to reach a certain rotation capacity. The hybrid beams showed a bit higher rotation capacities, and our numerical model, including the plastic material and damage behavior, have been created and validated. And also the rotation capacity is depending on especially the cross-section dimensions and the system geometries. As outlook, our validated models can be used to conduct extensive parametric studies, to extend the database, especially we can analyze the cross-section geometries, influences, the Sneller's limits, material properties, and finally derive design recommendations for the plastic design with HSS. Thank you very much. If you have any questions or feedback, feel free to contact me.